Hello viewers, today we shall start our discussion on interfacing of input-output devices. As you know, you cannot build a complete system without input-output devices or peripherals. Just like a human being cannot do anything without the various organs. So we have to interface different types of input-output devices to the microprocessor or the CPU to build a complete system. And in this lecture, we shall start our discussion how it can be done. We have already discussed how memory devices can be interfaced to the microprocessor through the system bus, and then we shall discuss today how input-output devices can be also interfaced through the system bus. In the last lecture, we have briefly mentioned about the difference between memory interfacing and I/O interfacing and why I/O interfacing is so different. First of all, you will see that I/O devices have wide variety of types. For example, some of them are mechanical, some of them are electrical, some of them are electromechanical, some of them are electronic, and so on. Some of them are optical. So the technology is different. So in case of the interfacing of memory devices, in spite of the fact that memory devices are made of the same technology, same VLSI technology, there are some incompatibilities. Obviously, whenever you have I/O devices made of different technologies, obviously the possibility of incompatibility is much more, and you have to use extra hardware like transducer, AD converter, DA converter, relay, optocoupler to bridge this gap. Secondly, we have mentioned about the wide range of speed. In case of memory devices, although the memory devices are not of the same speed as the microprocessor, but the speed difference is not really much. We can manage it by using few wait cycles, as you have seen in the last lecture. But this cannot be done in this case. For example, there are some devices where the data transfer rate is only few bytes per minute, several bytes per minute, and it varies from several bytes per minute to few megabytes per second. There are some input-output devices which are pretty fast, where the rate of transfer can be few megabytes per second. So you can see several order of magnitude difference in speed or variation of speed. So we have to develop technique such that so that we can overcome this rather the data transfer can take place efficiently in spite of this wide range of speed variation. Finally, we have mentioned that there is wide variation of data formats. Some of the I/O devices are inherently serial in nature. By that I mean the data is generated bit by bit. For example, whenever you read data from a from magnetic device, usually you are reading in serial form, or whenever you are receiving data from some telephone line or satellite, there also you are receiving in serial form. So we have to use serial to parallel and parallel to serial conversion if we want to communicate with these I/O devices. And also there are some differences in formats of data. As you know, you have to use different types of data types, numbers, characters, and so on. Usually for representing characters, ASCII code is used, 7-bit ASCII code, which is 7-bit. However, there are some devices where Hollerith code is used, which is a 12-bit. So Hollerith code also represents alphanumeric characters, however, with the help of 12 bits. So depending on which format is being used for representing the alphanumeric characters, you have to do conversion of codes whenever necessary. So we have to bridge these gaps, and obviously the uh, the interfacing problem is more difficult because of the severe difference in uh, speed, uh, technology, and data formats. So the level of incompatibility is much higher in case of input-output devices, and we can overcome that by using suitable techniques. First of all, we have to develop different types of modes for data transfer so that the speed incompatibility is overcome. We can communicate with slow devices as well as fast devices efficiently. Let us discuss about these modes of data transfer. The data transfer techniques can be broadly divided into two types. Broadly divided into two types. One is known as serial, when you are transferring data in bit serial form. Another is parallel. Parallel means you are sending in terms of bytes or words. So data transfer is possible both in terms of uh, bytes in parallel form or in serial form. Again, whenever you are sending in serial form, we shall see there are two alternatives available. One is synchronous and another is asynchronous. So, so far as serial is concerned, you can transfer in both the ways. Later on, we shall discuss about it in more details. Similarly, the parallel mode also has several alternatives. For example, broadly it can be divided into two types: programmed I/O, where you will be transferring data by using a program. That means for transfer of each byte of data, you will require few instructions. So that's why you are calling it programmed mode of data transfer. On the other hand, you will see that programmed mode of data transfer has some limitations. It is slow in nature because you will require few instructions to transfer only one byte of data. So another alternative method is known as direct memory access, DMA mode of data transfer. Later on, again, we shall discuss it in more details. Now, the programmed mode of data transfer has, again, a number of alternatives. Number one is synchronous. Second one is asynchronous. And third one is interrupt driven. Sometimes this interrupt driven is not considered as programmed I/O, but I believe the interrupt driven mode should also be categorized as part of the programmed I/O, because in interrupt driven mode of data transfer, the data transfer takes place with the help of a program uh, that we shall see in detail later on. Now let us consider each of these modes one after the other. Let us start from the bottom: synchronous mode, followed by asynchronous mode, followed by interrupt driven mode of data transfer. So the synchronous mode of data transfer can be performed only when the I/O device is compatible in speed. Compatible in speed. If the I/O device is compatible in speed, as we have seen in case of memory devices are usually compatible in speed because they are manufactured by the same technology, same VLSI technology. In such case, the data transfer in synchronous mode is possible. So usually, the data transfer with memory takes place by using synchronous mode. And synchronous mode not only can be used in case of compatible devices, compatible in speed devices. There are another possibility: if the speed characteristic is precisely known, if the speed characteristic is precisely known, then also we can use the synchronous mode of data transfer. Let's see how it can be done in the first case. Let us represent the operation of synchronous mode of data transfer with the help of a flowchart. We start, then we will simply execute IO instruction. So that's the simple operation you have to perform. You have to execute an instruction to transfer the data, to execute the IO instruction so that the data transfer is complete. Then you will stop. On the other hand, whenever uh, the device is not compatible in speed, but the speed characteristic is precisely known, then you can use somewhat similar technique but little different. Start. In this particular case, you will send get ready signal. Here by get ready I mean usually you are sending the address, then the chip select signal for that input output device. That actually acts as get ready signal. Get ready signal to IO device. After that, since the device is slow, as we know, then you have to wait for some precise time. So we will generate some delay. We will generate some delay. How delay can be generated, you already know. So you will wait for some more time till the device is ready for transferring data. Then you will perform execute IO instruction. Then you will stop. Uh, and it has been found to be very simple. Let me explain the synchronous mode of data transfer by a simple real life example. Suppose you have to boil a pot of milk. If you precisely know the time required for boiling the pot of milk, what you can do, you can go to the kitchen, put the container on the oven, turn the oven on, then after the precise time, let's assume 15 minutes. After exactly 15 minutes, you will remove that pot from the oven. Since you know that the milk will take 15 minutes to boil, exactly after 15 minutes, you will remove it from the oven without looking into the milk. That means you are not looking at the status of the IO device. You are not checking whether the milk has boiled or not. So here you see we are not considering, not looking at the status of the IO device. So this is your synchronous mode of data transfer, where the status of the IO device is not checked. So, but unfortunately, this cannot be used when it is when the IO device is not, I mean, it is not suitable. This technique is not suitable when the speed characteristic is not known. Of the IO device is not known. Let us go back to our real life example. You know, the time required for boiling a pot of milk, maybe 1 liter, may take different time, different amounts of time, depending on the ambient temperature, depending on the shallowness of the vessel, of the container, depending on how much water has been put by the milkman into the water. Because of various reasons, the exact time required for boiling the milk may not be known. In such a case, what you do? What you normally do, you keep on checking whether the milk has boiled or not. After putting the milk on the oven, you will see, has the milk boiled? Has the milk boiled? That you will keep on checking that. That is asynchronous mode of data transfer. Whenever you are transferring data, after checking the status of the IO device, after the device is ready for transferring data. Let's see how it can be done in case of computer. So this asynchronous mode is suitable when timing characteristic are not known. How it can be done? Let me again illustrate with the help of a flowchart. So we start. Then you will send get ready signal in the usual way by sending the address and the chip select signal to the IO device to the IO device. And this essentially what you are doing, you are sending a hardware signal, you may call it request. You are sending a request signal. Where you are sending? You are sending it to the input output device. And after that, what you will do, you will check, is the device ready? Just like, has the milk boiled? Has the milk boiled? You will keep on checking whether the device is ready or not, ready for data transfer or not. So if the answer is no, you will keep on looping. And if the answer is yes, then you will come out of the loop and you will execute IO instruction. And then you will stop. Now you may be asking how the device informs that it is ready. In such a case, a signal will come from the IO device, and this signal may be called as acknowledgement, say ACK. Acknowledgement is coming from the IO device. So here you see the microprocessor or CPU is sending a request signal to the IO device. In response to that, whenever the IO device is ready for transferring data, then it is sending an acknowledgement signal. So this is usually known as handshaking signals. Handshaking signals. And that's why this asynchronous mode is also known as handshaking mode of data transfer. The CPU is sending a request, the IO device is sending an acknowledgement. So you require two hardware signal, one going from CPU or the microprocessor to the IO device, another is coming from the IO device to the microprocessor. Now, what is the advantage and disadvantage of this technique? The advantage is that this particular mode of data transfer can be used even when this peak characteristic is not known. However, it has got some disadvantage. What are the disadvantages? First of all, you see, whenever you are looping here, you are essentially the CPU is executing instructions. That means the CPU time is wasted just to check the status of the IO device. So the precious CPU time is wasted. Obviously, our modern housewives are so busy nowadays, they will not like to look at the milk for a long time and to check whether the milk has boiled or not. So here also the CPU time is unnecessarily wasted. How do you overcome that? In case of our real life example, what you can do, we can buy a milk cooker and put the milk in the milk cooker, put it on the oven and forget about it. Then we can do something else. We can read book, we can attend some guest or write some program in the computer. And when the milk is boiled, it will generate a whistle, an interrupt signal. So to overcome this problem, we can go for interrupt driven mode of data transfer. But before coming to this interrupt driven mode of data transfer, I think I should give an example of asynchronous mode, which you have already used in case of your uh, data transfer with memory devices. There you have seen the microprocessor is connected to the memory devices, and this is your memory. And memory may be slow, may be compatible in speed, may not be compatible in speed. We have already seen how a slow memory can be interfaced to the microprocessor. And there we have seen that there is a ready signal uh, which is coming to the microprocessor. So this is the ready signal. So this chip select along with this address may be considered as the signal going from the microprocessor to the memory as a get ready signal. And when the memory is ready for data transfer, then this ready signal goes to the microprocessor. So this particular mode, when I discussed, this can be considered as asynchronous mode. And as a consequence, as you know, you can generate few wait cycles. So this is your T1, this is your T2, and then you can generate wait cycles, because by making the ready line low here, starting from here, if you make the ready line low, then you can have two wait cycles, and after that if it goes up, then of course there will be no further wait cycles. So this is your ready and this is your clock. So you can insert, as you have seen, this is the extra time you have allowed for interfacing with slow memories. And then T3, you are transferring data somewhere here. So you see this asynchronous mode of data transfer was also used in case of data transfer with slow memories. And this technique is widely used in case of IO devices, but it has some limitation, as I told, and this is overcome by using interrupt driven mode. Let us try to understand how in a microprocessor we use interrupt driven mode of data transfer. As usual, let me explain with the help of a flowchart. And the CPU sends get ready signal to the IO device. This is same for all cases, because the CPU always starts data transfer by generating the address, which in turn is used for generating chip select. So this is going to IO. So it is going to input output devices. And the IO device will receive the signal, it will try to get ready. But the CPU will not wait for that. CPU will keep on fetch and execute instructions. It will keep on fetching and executing instructions until when? Until there is a interrupt. Whether there is an interrupt, is there any interrupt? Any interrupt? So it keeps on checking whether there is any interrupt or not. How it is checked? It is built in as part of the function of the control unit of the processor. We have already discussed about it. Let me go back to the state transition diagram. There we have seen, after executing each instruction T1, T2, T3, T4, It is checking whether it is last machine cycle of the instruction. That means after the last machine cycle of the instruction is executed, the processor automatically checks, it is built in as part of the hardware. It checks whether there is a valid interrupt or not. If there is valid interrupt, it sets the interrupt acknowledge flip flop. Then it jumps to interrupt service subroutine. It does not. Uh, that is also an execution of instruction. But you see here, the after each execution of instruction, the interrupt is checked. So here also the interrupt will be checked, and then it will save processor status. As you know, we have to, whenever there is an interrupt, then processor status is saved and jump to subroutine, jump to, in this case we call it interrupt service subroutine, ISS, interrupt service subroutine. So this is taking place in response. It comes out of this in response an interrupt coming from an IO device. So here you see some kind of hardware signals used. One is when you are sending get ready signal to the IO device by using a hardware signal. Usually it is chip select and the address information, address signals going to the IO device. And here an interrupt is coming. In case of 8085, as you know, you have a number of interrupt lines, 5.5, 6.5, 7.5, INTR, and so on. Any one of them can be used as an interrupt signal coming from the IO device. And after it, what it does, it jumps to that interrupt service subroutine. Let's go to the interrupt service subroutine. And this is that interrupt service subroutine. Start. What it does, sometimes some of the registers are being used by the in the main routine. So you push the processor status. In this particular case, here by processor status means the program counter and accumulator and the program status word is saved. But if more registers are used, that you have to save here. After doing that, you will perform that data transfer. Execute IO instruction. After execution of IO instruction, what you will do? You will restore processor status. You will pop up the register values. You will restore the processor status. Then you will return from the subroutine. You will return. Where you will return? You will return back to this point, to this point. You will go back to this point, and then you will keep on fetching an instruction. It is like this, that this is the main program. Let's assume this is your main routine, and as part of this is your main routine, let's assume, and it was executing. At this point, a data transfer was required, so it initiated data transfer, and then when an interrupt comes, it jumps to that interrupt service subroutine, and after the interrupt service subroutine execution is over, it comes back, and again it resumes instruction execution. So in this particular case, as you can see here, there is no wastage of precious CPU time. CPU, after initiating the data transfer, keeps on executing instructions, and only when the IO device is ready, it generates an interrupt. Then only the CPU comes out of the main program, as we have seen here, and then performs the data transfer as part of the interrupt service subroutine. So this is how interrupt driven mode of data transfer can take place. Now in all these cases, whether it is asynchronous mode or interrupt driven mode, you will require few instructions for data transfer. And particularly if you are transferring data from some IO device to some memory devices, you cannot do it in single step. You have to transfer first from the IO location to the accumulator or one of the microprocessor registers. Then from the register you have to transfer to the memory location, and vice versa. From memory also you have to transfer to the CPU register or the accumulator, and from the accumulator you have to transfer to the IO device. And as a consequence, the program mode of data transfer, particularly whenever you have to transfer a block of data, large volume of data between IO device and memory, these program mode of data transfers, the asynchronous or interrupt driven or synchronous, are not really suitable. So in such a case, we have to go for what is known as DMA mode of data transfer, direct memory access mode of data transfer. Let me explain the basic scheme, and then we shall illustrate with the help of the flowchart. As usual, this is your microprocessor, and this is the system bus. To the system bus, your main memory is connected. All are hanging memory devices and IO devices. And on the same system bus, uh, several other devices are also hanging, a number of IO devices. Although I have shown here only one memory device, it can be a number of memory devices, a memory bank, static and dynamic RAM, and this is your system bus. To implement DMA mode of data transfer, you require a special hardware, special device, special IC chip known as DMA controller. And the IO devices, this is one IO device. IO device 0, let's assume, and this is IO device 1. And this DMA controller is connected to each of these IO device. With the help of IO device, can request for DMA mode of data transfer, and also whenever the DMA mode is granted, there is an acknowledgement. So request and acknowledgement. So that is coming from each of the IO device. A particular DMA controller can provide DMA mode of data transfer to a number of devices. So this is again request, and this is grant or acknowledgement. In turn, the DMA controller also has a DMA request, and there is a grant signal. As you can see here, the DMA controller is receiving requests from a number of input-output devices, and obviously at a time DMA can be granted only to one device if more than one IO devices request for DMA, and that has to be resolved by using an arbiter. Later on we shall discuss in detail about this DMA controller, how it works, how this arbitration is done. Right now let us focus on how DMA mode of data transfer works. And this request goes to, for example, if it is 80 microprocessor, this is your hold DMA request, and this is your DMA grant coming out from the microprocessor. So this is your 8085, let's assume, for simplicity. So for DMA mode of data transfer, you require a special hardware known as DMA controller, which is acting as an intermediary between the CPU and the input-output devices. To explain how data transfer take place under the control of the DMA controller, between input output device and memory device directly. To illustrate that, let me take help of this flowchart. Start. Then a DMA controller will have several registers inside it, which are to be initialized, where you have to specify what is the starting address of the memory, how many bytes are to be transferred. All this information are to be initialized. So you have to execute, you have to initialize the DMA controller. Later on we shall discuss more in detail about it. So the first block will implement this, and after that it will send get ready in the usual way to IO devices. And here this is a hardware signal going to input output devices. After doing that, just like the CPU does fetching and execution of instruction in case of interrupt driven mode, here also it will keep on doing fetching and executing fetch and execute instruction. Fetch and execute instructions. It will keep on doing that. Until when? Until when there is a DMA request. Again, we go back to that state transition diagram. Here we see while executing instructions, it keeps on checking at several points whether there is a DMA request here, after T2, after T4. So you see, even before the instruction execution is over, I mean in between, in the middle of instruction execution, it checks whether there is a DMA request. If there is a DMA request, it jumps to it goes to that hold mode, T hold mode. After setting that flip flop, it goes to that. You can see here it goes to this hold mode. This hold mode is essentially during this period until this DMA request is granted, it remains in that. What does it mean? Whenever it is in this tri-state mode, the CPU relinquishes control of the system bus. That means it disconnects. And during that time, the DMA controller becomes the master of the system bus. So during this period, the microprocessor tri-states the address, data, and other control signals. And then DMA controller will generate those signals. So DMA controller becomes the master of the bus. And it will select the device, it will also select the memory location, and directly data transfer can take place as illustrated with the help of this flowchart. So is DMA request, so is there any DMA request received, or is DMA request active, which I have shown with the help of that state transition diagram. If the answer is no, it keeps on fetching and executing instruction. However, if the answer is yes, then it, as you have seen, it generates DMA grant signal. DMA grant signal is this one, hold acknowledge. This is the DMA grant signal which is received by the DMA controller. So here a hardware signal is generated by the microprocessor and which goes to DMA controller. So this has all these things have happened, but I have not. Let us focus on the IO device side. So IO device was initiated. That get ready signal was initiated. So what it does, the I/O device when ready sends DMA request to, it does not DMA request directly to the CPU, but it sends DMA request to the DMA controller. As we have shown here, you can see the DMA request is going from the I/O device. So the CPU initiated the data transfer. Then when the I/O device is ready, it sends the request to the DMA controller, as it is shown here. So the DMA controller will analyze the request with the help of its arbiter, and whenever the DMA controller decides that DMA request is valid, DMA controller sends DMA request. So this goes to microprocessor, and as a consequence of this, this whole line becomes 1. This is coming from the DMA controller to the microprocessor, as we have shown here. So I/O device sends DMA request to the DMA controller. DMA controller in turn requests the DMA request to the microprocessor with the help of this signal. And when the microprocessor is ready, it sends the DMA grand signal to the DMA controller. Then obviously the DMA controller will perform the data transfer. This is the job of the DMA controller. So you see the 3 devices. This is part of the CPU, this is the job of the I/O device, and this is the job of the DMA controller. It will perform block. So obviously this is not suitable for 1 byte. This is suitable only when you have to transfer a block of data. And withdraw DMA request. So after the data transfer is over, it will send that, it will withdraw the DMA request. That means this DMA request is withdrawn. After the block, you see during that mode, it will generate the address and it will also select. As if you may recall that, I mentioned about why there does not exist an instruction for data transfer between a memory and I/O. The reason for that is CPU cannot directly select a memory device and I/O device because it can generate only one address. But DMA request can select a I/O device with the help of this signal, can also select a memory location by generating the address, and after that through the data bus the data transfer can take place byte by byte directly between I/O device and memory devices. That's why we are calling it direct memory access, DMA, and it is pretty fast. Per clock cycle or per machine cycle, 1 byte of data will be transferred. You don't have to execute few instructions. Just in 1 machine cycle or in 3 clock cycles, 1 byte of data will be transferred between I/O device and the memory device. So this is how the uh, uh, the the block of data transfer is performed with the help of the DMA controller. So this shows how we can perform DMA mode of data transfer. Now we have discussed several schemes, several protocols you may say, synchronous mode, asynchronous mode, interrupt driven mode, DMA mode of data transfer. You have to implement these protocols with the help of a special device known as I/O port. Let me briefly introduce to you what do we mean by I/O port and why I/O port is necessary, and then we shall see how the I/O port can be used to implement different modes of data transfer. An IO device cannot be directly interfaced. This is your IO device. It cannot be directly interfaced to the CPU or the microprocessor because of various reasons. For example, we have seen that if you want to interface a memory device to the system bus, it must have the necessary built-in logic for tri-stating, because at a time only one device will be sending data to the data bus. So whenever a IO device is not selected, then it cannot withdraw from the data bus. So bus contention will arise. Usually IO devices are not equipped with that tri-state buffers, tri-state drivers. Moreover, device selection logic is usually not present in IO devices. IO devices are also not equipped with those handshaking signals to be generated by the, required for performing asynchronous mode and interrupt-driven mode of data transfer. So all these gaps are filled up by a device known as IO port. This is your IO port chip. So this is acting as an intermediary between microprocessor and IO device. How it is connected? This is the system bus of the microprocessor. System bus will not go directly to the IO device, but it will go to the IO port. And the IO port can be selected with the help of device selection logic. That means some of the uh, register values inside this will be mapped on the IO address space. Device selection logic. So it will generate that chip select. Now, what it should have? First of all, it must, this IO device, this IO port must provide bus compatibility. Because it has to be directly interfaced to the system bus of the microprocessors. So the IO port chips are realized. It is also a IC chip. It is implemented as a bus compatible device. All the address lines, some address lines, data lines, some control signals, it will be able to receive. Then it has got the tri-state buffers, tri-state buffer. That means whenever this chip is not selected, then this will be tri-stated. This IO port will tri-state the inputs or outputs, so that it does not affect other devices which are connected to the system bus. It will also have device selection logic, as you have seen here. This is by which it can be selected. So device selection logic. It will also require some buffers inside the chip, because the rate at which data transfer take place between the microprocessor and IO device is not same. So at high speed, the microprocessor will send data to the IO port chip, which will be stored here. Then from here it will be transferred to the IO device through another bus. And so it will require data buffers, and also it will require some control. It will be a programmable device, so it will require some control register and status register. Then, as we have seen, whenever you are performing handshaking mode of data transfer or interrupt driven mode of data transfer, you will require several hardware signals. So here you see the handshaking signals will be generated by the IO port. So this is the request which is going to the IO device. An acknowledgement signal coming from the IO device will go to the IO port. Then the IO port will transfer data with the microprocessor chip. So handshaking signals will be required, and for performing interrupt driven data transfer, a signal will go from the IO port to the microprocessor. This is the interrupt signal. So you see, to facilitate asynchronous mode data transfer, you require handshaking signal. To facilitate interrupt driven mode of data transfer, you require interrupt signal generated by the IO port going to the microprocessor. And handshaking signals, interrupt signals should be generated by the IO port. And IO port chips are available in two types: non-programmable and programmable. In the next lecture, we shall discuss about the different types of IO ports, non-programmable and programmable. Usually programmables are more versatile, and we shall discuss in more detail about it, and we shall see how different types of data transfers are implemented with the help of these programmable IO port chips. Thank you.